Let us assume this pipe is solid and rigid, and the fluid inside this pipe is incompressible fluid, which means the density is same whether it's in this section or in this section. It is the entry side and it is the exit side, and the cross-sectional area in the entry side is A1 and cross-sectional area in the exit side is A2. Let us assume we push some amount of water to the right side in section of entry. We can predict that the same amount of water, which means same volume of water, would be exiting out from the exit section, and it would be longer than this section because it compensates for the area. The volume of this section V1 equals A1 times D1, A1 D1. Volume in this section, the exit section, would be A2 times D2. We know the density equals mass by volume. Then the mass equals density times volume. So the mass of this section would be M1 equals density of this section rho times the volume of this section V1, which would be equals to rho A1 D1. Mass of this section would be M2 equals similarly rho A2 D2. And notice that the density is same because it is the same liquid, and we considered incompressible liquid, so that means the density in this section is equals to the density in this section. And if you look at the conservation of mass, it states that the mass flowing in any time must be equal to the mass flowing out in that same amount of time. It means if m mass is entering in t time in this section, the same amount of mass should be exiting in the same time from this section. So that means m1 over t in the entry must be equals to the m2 over t in the exit. And we know m1 equals rho a1 d1 and m2 equals rho a2 d2. And if you look in this equation, d1 by t would be the velocity in the entry side and d2 by t would be the velocity in the exit side. We can also write this equation as rho A1V1 equals rho A2V2, which means density, area, and velocity. Notice that this is the not volume but the velocity. Volume is represented by this capital V. The density can be divided both sides. This leaves us with A1V1 equals A2V2, which is the continuity equation. And if you want to know what that actually means, is that if I push some water in this section, in the left section, the same amount of water should come out of this section. But we know the area in this section is larger than the area in this section. The water must flow out quickly in this section compared to this section, so velocity should be higher in this section to compensate for its area. So if the area is larger, the velocity would be smaller. And if the area is smaller, velocity should be larger to compensate for this area. Because mass flow rates should be same in both sides. Because it has nowhere to go except this exit side. It would have been the different case if the pipe had some holes or had some source in it. But this pipe is very solid and rigid, so it does not have any holes or any sources of water. So what goes in must come out. So therefore A1V1 equals A2V2. We can also represent it as this way. AV equals constant. That means if area is higher, velocity would be lower, and if area is lower, velocity would be higher. Thank you.